Good afternoon, everyone. Thank you for joining our guest lecture at Penn State. So today we have great pleasure to welcome Professor Xu Han from University of Notre Dame to introduce the research we did in the data center modeling. So this is a joint project we did a few years ago when she was my PhD student. Xu, without further ado, maybe you can start your lecture.
Okay, yeah, thank you, Professor Zhou, for the kind invitation, also the kind introduction. Can you see my screen,
Yes.
the slides? Good.
Yeah.
Okay. Um, so my name is Xu Han, currently assistant professor from the University of Notre Dame, and so today I'm really excited to introduce a project we did for modeling and optimization of data center cooling systems. Okay, let's get into it. Okay, so this project is funded by Department of Energy. It's called Improving Data Center Energy Efficiency through End-to-End Cooling Modeling and Optimization. So the PI is Dr. Wanda Zhou. Co-PIs include Dr. Michael Witter from LBM and Jim Mangelder from Schneider Electric. So this project was organized with three modules. The feature one is the optimization of the cooling system, and feature two is the airflow and thermal management, basically this CFD study. And the module three is the holistic optimization, including all the cooling system and also the airflow management together. And so today we will be focusing on the first one, the feature one, the cooling system modeling. And I was a graduate research assistant um, when I participated in this project in Dr. Wanda's research group at CU Boulder. We followed a four-step workflow for this project. So firstly, from the very beginning, data collection, right? We define the system boundaries, right? Gathering all the information like equipment information, control logics, all the information. And then model implementation, we choose the model fidelity and we develop the modelic models from like components to system, also including all the controls. And then after finishing implementation of the model, we calibrate the model with the collected operational data. And then we validate the model. And after that, we use the model to perform some model-based study, for example, to evaluate some different energy efficient measures. Okay, this is a workflow. And so this is a data collection. So, data collection is the foundation of almost everything. So especially for real world project, this is not like your homework or like a course project. You will be given all the information, for example, all the assumptions. But for real world project, you really don't know for example, what is the um, equipment, right? What is the size and what is the nominal power, like performance curve? All of this you need to collect. Okay. And so based on the data collection, we prepared a report for a summary of everything. So here is a snapshot for the report. You can see they include, for example, the general information like the layout of data center, and some design information like a chiller, pump, cooling tower, air handling unit. Also the control logics, including supervisory controller, some local controllers. We'll talk about those later. And also some operational data we collected. And so here you can think about one question: what are the sources for collecting this information? Okay. And so when we did this project, the sources we used for data collection includes, for example, the document and product menu, right? Also the drawings. We got all the drawings, like mechanical drawings, electrical drawings, and also we look at the control source code. Okay, I will show you some examples. And we also consulted the building operators because they are the guy who really know the system, right? They control their system configurations. And we also had on-site visit to do some experiment. For example, we measure their airflow or something. We do some experiment. And so here is a one example of the data collection report. This is a summary of the equipment of primary pump here. For example, in this table, you see we documented the information of like a nominal mass flow rate, right? Nominal head, nominal power, and also this is a performance curve, right? And for the control logics, of course, we got some information from the joints, right? The configurations, those control point. And but for the detailed control logics, we extracted from the control source code. So this is the control source code I just mentioned. For example, if you see the if something for a condition, then they do this, right? This is the original source code of the control. They are probably um, 50 or 80,000 lines of code. And of course, we didn't read them one by one, right? One line by one line, but we basically researched the keyword. For example, the air handling unit or the chiller or the supply water temperature. We search the keyword and then we can locate the source code for all of these control logics. And so this is a data center we was working on. So this is a real data center located in Massachusetts. It's 5A climate zone code, cool and humid, and the cooling system is configured with chilled water system with air side economizer. And if you're not familiar with data center, so here this is a code IO. So you may have heard the term, right? Code IO. So basically for data center, this is the air-based cooling data center. The chilled air is supplied from these perforated tiles on the floor here. And then the chilled air will go through the IT racks and then bring all the heat dissipation away from the IT servers and then exhausted to the hot IO. So you see there are multiple rows of the IT racks. So here, this is cold IO. They supply the chilled air from the cold IO and then exhaust the hot air from this hot IO. Okay. So, and then eventually go back to the like a ceiling plenum and then eventually go back to the air handling unit. Okay. And this is some pictures of the data center, and we had some on-site visit. And this is the cooling system configurations. Um, this is a pretty conventional cooling system with two chillers and two cooling towers and water pumps. This is a condenser water loop. This is chilled water loop. And this is air handling unit. They have two AHUs, and they also have a mixing box, so they can introduce the out air to do free cooling, okay, when the weather is cold. And this is a handling unit. So here is schematics of the cold IO and hot IO I just mentioned. For example, this is underfloor plenum. The chilled air goes through here. This is perforated tile and go to the cold IO and then go through the rack and go back exhausted to the hot IO. Okay, and then go to the ceiling plenum. Eventually go back to the AHU. Okay, and so initially, when we built the mathematical models for such a system, the first step is we identified all the components needed. For example, of course, we need chiller, right? Chiller, cooling tower, uh, water pumps, pipes, AHU, and rooms, right? So we need all this component. And we also need some control, right? We extracted all the control, very detailed control logics. So we need to implement those control logics, right? So the controls. So here, you can think about what models can be obtained from the open source library, like a Modelica business library, right? And which models should be customized. So here is the answer. So basically, at the time that we did the project, so the chiller with two variable speed compressors was not available, and the AHU with air side economizer was also not available. And some, of course, all the controls are not available because they are not a standardized control. We extracted from the control source code. They are pretty customized control logics. So all the control logics should be customized. Okay, and I will show some examples. So here are the component models we obtained directly from the Modelica business library. For example, the chiller compressor model. This is a part of the the model from the buildings library, and cooling tower model, and pumps model, and pumps and pipes and ducts model. Okay, we can directly have them. So actually, you can say this is the beauty of Modelica. You can take advantage of a lot of open source resources instead of building everything from scratch. So we can directly grab them. Okay, we can use them. And this is the room model we use. It's a very simple room model. If you know Modelica, you can see this is a mixing volume, right? This is just volume. This is heating source. Heating source can model mimic the heat dissipation from RT server, right? And then two ports, very simple, right? So you may find something was missing, right, in the room model. For example, the heat loss or heat gain through the building envelope, right, through the solar radiation, right, solar heat gain, right, all of this was not modeled here, right? So if you look at the equation, also you can see that clearly, right? This is a dT. This is the temperature of the mixing volume to dT. Is we only consider this is supply air. This is the internal heat dissipation from the IT server, right? So we did not consider any like heat gain through the building envelope. And the major reason is that um, it is negligible compared to the heat released by the servers, okay? Because they are too small, we just ignore those part. And also we have an assumption, the temperature of the air entering the IT equipment is equal to the underfloor plenum and the supply air temperature. This is our assumption for the model. Because in reality, this can be a little bit different because when the air is supplied to the cold aisle, it may be mixed with some ambient hot air. So it will be a little bit higher than the supply air temperature. Okay. So, but here we just assume they are the same. Okay. And but some of the models we need to customize in Modelica. For example, this is air handling unit with air side anemometer. Um, this is the AHU model, and this is the air-side anemometer model. And you know, the Medica is a hierarchical structure model, right? This is a top-level model. If you open this AHU module, you can see the detailed implementation of the AHU, right? For example, the fan, heating coil, cooling coil, and like the humidifier, okay? So this is the different sections of the AHU, right? And usually when we build a model, we have the input, we have the output, right? For example, the AHU model, the input can be temperature set point, for example, and also some control signal for the fan, control signal for the damper of the outdoor air, right? Those control signal are all the inputs of the AHU. And the output can be, for example, the power consumption, right? And also, for example, some temperature sensor may output the temperature information. Those can be the output. And this is another model we customized. This is chiller with two variable speed compressors. So now it's available in Modelica Business Library. So this is a model implementation. You see there are two compressors. So when there are two compressors, you need to consider the staging control, right? You need to consider when we should turn on one compressor, when should we turn on the second compressor, right? So it's like a staging control. The logic would be, for example, here, the second compressor will be on when the chilled water supply temperature is higher than the set point. That means they don't reach the set point, right? It's higher. And then we need more cooling, right? So the second compressor will be on. And of course, when the chilled water supply temperature is lower than the set point, that means we have enough cooling, right? So the second compressor can be kicked off, right? So this is a control logic. So once we have the control logic, and then we can start to do the implementation. For example, this is the detailed implementation for the staging controller, which is here. This is a block. So if you open this block, we can have this detailed implementation of the staging control. It is a very typical state graph model. Basically, we have different states like off or stage one, stage two. Stage one is one compressor on, stage two is two compressors on. And And here is the switching condition. For example, this is switching condition from one compressor to two compressors, right? So this is a the place we can define the switching condition, right? You see, we can write down the equation here, like a T minus T set, if it is greater than the set point, for example, or than like a threshold, and then we can switch to stage one to stage two. Okay, this is how we implement this switching conditions in a staging control. Okay, and this is a summary of all the control logics. Because this is real world data center is fairly complicated. Um, for example, this system level control determines the cooling mode, like a mechanical cooling mode, like a free cooling mode. And this is equipment level, like a air loop, chilled water loop, and condenser water loop. And if we look at for example, the chilled water loop, that have the evaporator flow control, chiller stage control, because we have two chillers, right? Chiller staging control and chilled water supply water temperature control, right? The pump stage control, differential pressure control. So all of the controls, they are all connected with each other, right? And for a temperature control, for example, the air loop temperature control, because we have many different control point for temperature. For example, for data center, we have the underfloor plenum air temperature control, and we have supply air temperature control, and we have mixed air temperature control, and also reheater control. So to figure out all of these control logics and also their relationships, um, it's not an easy task, but we need to make everything clear before we can implement those. And I can give you some example how we implement those control at different levels. For example, this is system level control. Um, there are three different cooling mode. FC is free cooling mode, and PMC is partial mechanical cooling mode, and FMC is fully mechanical cooling mode. So we also extracted all the switching conditions. For example, the free cooling mode will be switched to partial mechanical cooling mode when the outdoor air dry bulb temperature is higher than the floor temperature set point, and the outdoor dew point temperature is greater than the lower band of the outdoor air dew point temperature. Okay, this is a switching condition. Okay, and this is another switching condition to switch from the PMC to the fully mechanical cooling mode. Okay, and here I'll give you an example how we implement this logics in Medelica. Okay, uh, again here we also use the state graph model, right? Three modes: FC, PMC, FMC, right? And are the inputs of this model. For example, we may need the input from supply air temperature set point, right? And the outdoor dry bulb temperature, because the switching condition, right? We need this data, right? So the dry bulb temperature, also dew point temperature, right? We also need this data. And the air temperature, return air temperature, we need it here, right? Let me see. Return air temperature. Yeah, this is here. RA is return air temperature. Okay, so this is the input of the control module, and so what we can do is this is a block to define all the switching condition. Okay, for example, this condition can be defined here. This is switch from FC to PMC. Okay, and so after implementing all the control logics into the all the switching condition module here, and we finish this model. This is a system level controller, okay? And for the component level control, because they are connected with each other, so it is fairly complicated. I can give you some example. For example, this is the this underfloor plenum air temperature control. So basically, we will control the temperature at the underfloor plenum. So here, UPAT is here. And this temperature, this control signal will be served as input of a mapping module to reset the supplier temperature set point. So what does this mean? This means, for example, if we want to, for example, if the underfloor cleanup temperature is very high, and how to lower its temperature? We need to, for example, we need to lower the supplier temperature, right? So this is the reason the control signal here will be used to mapping the supplier temperature. So basically, they are connected, right? And the supplier temperature set point will also be fit into the, of course, the PID controller for the supplier temperature control, right? This is a set point will be fit into here. And this supplier temperature will also be used, the control signal will be used to manipulate the MAT control, the mixed air temperature control. Because, for example, during the free cooling mode, if we want to lower the supplier temperature, what we can do is we can probably introduce more outer air, right, to lower the supply temperature, okay? Or we need more chilled water. This is another loop, okay? So this is the reason why the control signal of the SAT will also affect here the supply, the chilled water supply temperature set point, okay? So let's see how we implement this, okay? This is the control module we implemented for the air loop, okay? It looks very complicated, but if we categorize this into 4 groups, you see the first one on the top will be the supply air temperature control module. And here is the mixed air control module. This is a chilled water supply temperature control module. This is a heater control, okay? If you look at it one by one, for example, we just give you one example. So here, this is the PID controller number 1. This is for the UPAT over here, right? It takes 2 signal. One is the set point, one is the actual measurement, okay? And then the control signal is fed into the mapping here. You see the mapping here to reset the supply temperature set point, okay? This is how we implement this control logics. So you see, it is really critical to draw the schematics clearly so that you can follow the structure for the implementation in Modelica. And this is the implementation for some other controls. We won't be able to go through all of this here, but you can read our paper. We have had a paper for this case study. And this is for the air loop. And for the condenser water loop, the condenser water pump and the cooling towers are staged based on the number of operating chillers. For example, if one chiller is on, one condenser water pump and one cooling tower should be on. So they should be consistent. And the condenser water supply temperature set point is reset within this range, and based on the outer air wrap up temperature within this range. So this is like there's a mapping algorithm, okay? And the speed and number of the operating fans in the cooling tower are manipulated to control the condenser water supply temperature at its set point. And let's look at their control. This is the condenser water loop controller. So they take for example, the chiller on signal and the web up temperature, cooling mode, also condenser water supply temperature as the input, right? And then they have the controller. For example, this is a controller for the condenser water temperature, okay? And basically they have the fan staging control, they have the fan speed control. And if you further open the fan speed control, so essentially this is a PID control, right? They basically take the signal of the condenser water supply temperature and their set point, take these 2 signal, right? And PID controller and generate the control signal, okay, to control the fan speed. And after we implemented all the component models, we can integrate them together to build the system level model. And here, this is the final model we developed. And you can see here is this is the schematics of the system configuration. This is magnetic models. There are two chillers, right? Two cooling towers and two air handling units. And here's the water pump. And here's there are two thermal zones. And all of these are controllers, okay? These are controllers, chilled water loop, cooling mode controller, condenser water loop controller, okay? And this is some equipment configurations information. Okay, so after we implemented the modality model for the system, so the next step is we want to know how accurate our model was, right? So we basically we do two two steps. One is we do calibration, right? We want to calibrate some parameters by minimize the discrepancy between the simulation and the measurement, right? We do the calibration first, and then we do the validation. This is like in the machine learning, we do training and we do then you do test, right? It's similar. So this is an example of how we do the calibration. And this is a cooling coil. So we fit this model with the supply air or supply water, or this is supply water temperature and mass flow rate. And then we have the model to predict the outlet water temperature. And then we compare this simulated outlet water temperature with the actual measurement. Okay. And then we want to minimize the error, right? This is normalized mean error, right? NMBE. So and then we would perform an optimization study. So we tune this parameter. For example, the cooling coil, we can tune the U value, right? We can tune the U value. So initially we had the nominal U value data from the product manual, but their actual U value can be degraded, right? So we calibrate those U value for cooling coil. This is an example. And so here is the calibration and validation results for all the components. Um, so in general, all the component model reach the calibration error within 80%. So this is pretty impressive because this is a real world project. All the data are collected from the site. And so in the next page, I can show you the time series data. So the pattern, you can see the training and the validation. Training is the calibration, and validation is the test. So basically, in both training and validation data set, the simulation, this is a simulation, and this is a measurement. They are in pretty good agreement with each other. So meaning our simulation model can capture the real dynamics pretty well. Okay, so until now we have the model completed and also validated. So the next step is how can we use the model, right, to really propose some energy efficiency measures, right, and to quantify something. And we propose multiple energy efficiency measures. So this is the first one is clean the degraded cooling coil. This is because what we found is that when we do the calibration, we found the nominal UE value is 77, but the actual UE value is just 30, 28 or 30. So that means the cooling coil was degraded a lot. So so immediately we thought about, okay, probably we need to clean the cooling coil, okay? And this is our first measure. And this is simulation results. So the blue color is the baseline without doing anything, right? And the yellow color is the with the retrofit by cleaning the degraded cooling coil. So what we found is very interesting actually. So it resulted in 76% more energy consumption. Okay, no any energy savings is more energy consumption. So and then we thought about okay, why? Then we look at the breakdown of the energy consumption, right? We found okay, most of the energy increase came from the reheater. Okay. And then we thought about, okay, what is the reason, right? Why much more energy was consumed for the reheater? And after some analysis, we found, okay, the fold cooling coil cool the supply air to around like a 21 degree. But the cleaned cooling coil can cool the supply air to around like a 18 degree. But the supply air temperature set point is 23. So that means the reheater need to be on to bring the temperature back to 23. So initially the fold of cooling coil, they just bring the temperature from 21 to 23. But with clean cooling coil, they need to bring the temperature from 18 to 23, which consume much more energy. Okay. Actually, this is problematic. We also propose other strategy to avoid this like a simultaneous heating and cooling, right? They cool the air, they also reheat the air, right? We want to try to minimize this. And also the additional heat generated by the heater also increases the thermal load. And so any potential problem, but so their data center actually was operated pretty well, even with like a 50% degradation of the cooling coil. But any potential problem with the degraded cooling coil, uh, they their operation was fine, mainly because their RT load is much lower than the design. So they never reach the like a peak load, the nominal designed peak load. So that should be fine, even with degraded cooling coil, right? Degraded cooling coil means their capacity is much lower than design, right? But it will be problematic to handle the full load condition, okay, which probably never happened to them, okay? Okay, so the first measure uh, is um, is um, is not, of course, not as we expected. Okay, then we try other energy efficiency measures. This is the second one. So after analysis of some simulation result, we found um, the because we have three modes: the fully cooling, free cooling mode, the partial mechanical cooling mode, and the fully mechanical cooling mode. We found the mode was barely stayed in the PMC, the partial mechanical cooling mode. And then we look at the reason. We found the reason was because they have the lower band and high band of the outdoor dew point temperature. Okay, they have a threshold, the lower band, high band. So this is really to control the moisture from, they don't want to introduce too much moist air from outdoor. So they have this like a threshold. But we found this lower band and high band are too close. One is 11.6, the other is 12.7. So if you really read their control logic, you found, okay, FC from FC to PMC is the actual dew point temperature is higher than the lower band, right? And then if it is higher than the higher band, it will switch to the fully mechanical cooling mode. So that means if these two numbers are too close, they can pretty easily switch from here to here, right? Because these two are very close, very similar. So what we propose is we increase the high band for the dew point outdoor temperature. Okay, and let's see the results. We found this measure can, without doing anything, we just change the set point. We can achieve 9% of energy savings. Okay, and this is the energy breakdown. So they can save the energy from the fan, from the chiller, right, from the condenser pump. And then if you look at the hours of different cooling mode, if you look at FC, the free cooling mode or the partial mechanical cooling mode, definitely uh, both the free cooling mode and also the partial mechanical cooling mode, their hours increased, right? So this is the reason why they can have this energy saving, because they took more advantage of the free cooling. Okay. But one potential problem is if you increase the threshold for this dew point temperature of outdoor air, one potential risk is the moisture, right? So we also double check their moisture to make sure they are within the recommended and acceptable range. Okay, and this is the detailed plot for the um, system dynamics. So for example, this one is the mode, right? You see the baseline, they stay in the fully mechanical cooling mode. But for the M2 measure, they can switch to the free cooling mode, you see? So this is the reason why they can save some energy, okay? But at the same time, the relative humidity is well controlled, okay? And then we propose another energy efficiency measure. It's called improving the supply air temperature control. So this is actually derived from the first measure because we found that do have the simultaneous heating and cooling, right? They cool the air to like a 21 degree, and then they use the reheater to bring back to 23. So what we found is that they lacked a two-way valve on the water side of the cooling coil. Okay, so they cannot change the water flow rate of for the cooling coil. So this is the reason why the air actually was overcooled. Okay, and so we propose to add a two-way valve, and then we can regulate the valve position to maintain the differential pressure to avoid the oversupply of the chilled water. And so by doing this, we can achieve about 9.4% of energy savings. Okay. And also the simultaneous heating and cooling is ruled out. Okay. And you see the AHU heater, right? This is a breakdown of the energy consumption. You see the AHU heater was basically illuminated because of this um, retrofit strategy. Okay. And so the next step is, okay, now we proposed three energy efficiency measures. We want to know what is the best and optimal combinations of this, right? Probably M1, M2, M3, right? Currently, what we evaluated is the individual EEM, right? And what we do is we use a called a sequential search optimization. So basically, we optimize the EEM one at a time, okay? For example, the first iteration, we just compare the individual EM, M1, M2, M3. And then the second iteration, we just pick the best one as the base, and then we add another one, okay? And then the second iteration, we can have the best combination of two EM. And the third iteration, we can add the third one, okay? This is called a sequential search, which is more efficient, but of course, probably is not as accurate as the exhaust search or some other um, like GA, right? Because the global search, but it's more efficient. If you do exhaust search, you need to evaluate all the combinations, right? It's more computational expensive. And this is the result. So our conclusion is the M2 combined with M3 is suggested, okay, saving like a 12% of energy. And M2, M1, and M3 is not suggested, okay? And so some industrial impact. So interestingly, the partner data center in Massachusetts, they investigated 110K to retrofit their data center based on our recommendations in the project report. So what they told us is that actually they received a similar suggestion from a consultant previously. So the reason why they didn't do the retrofit is because, the consultant, they had a lot of experience. By reviewing the drawings, the design, they can provide the advice, but because they didn't have any simulation model for this, so they cannot provide the number, okay, how much you can save by investing to retrofit this device, this equipment, right? But in our project report, this is also the beauty of modelic models, right? We can quantify the impact. For example, 10%, right? You can easily calculate the payback period, right? So, and this is some industrial impact. And we also have some other impact by releasing the open source models to the business library. and we develop many component models, control modules, and we published some of them in the buildings library, and which can be found in the magnetic buildings library buildings dot applications dot data centers. Okay. If you are interested, you can check it out. So here I just introduced the chilled water system model. And actually we also implemented the DX system. It's another type like a crown. You may heard the word, the crown, the crack, like a computer room air conditioner, the crack model. We also have those model implementations available in the magnetic buildings library. And so here's the conclusion. So the proposed model is calibrated, validated based on the measurement, and the model was utilized to identify the EM and quantify the impact. And the optimized EMs resulted in energy savings of 12%. Okay, this is our conclusion. Okay, thank you. And I'm open to questions. Any questions from the audience?
Thank you, Xu. Yeah, this is great to hear you remember all the details we did. Yeah.
Yeah.
Yeah, for the audience, I also post the link of the project website which has the reports and the papers resulted from this project.
Yeah.
Okay, any questions from the audience? If you prefer to speak out, just feel free to raise your hand. I see I can unmute you. Okay, that's one question from Bill. And he's asking, do you know who designed the existing control algorithms? Was it the data center technician or the equipment vendors, maybe?
I believe they should be the equipment vendors, not technician, I believe.
Yeah, the control is rather complex.
Yeah. It's not like a control code for the like a VV terminal box. The technician can write some code into it. It's a pretty complicated.
Okay, Victor's question. Link of resource. Okay, I can do it again.
Yeah, the link of the project.
Yeah. This is I just post a link of the project website. Maybe if you can click link on your end, we can show people what we posted there.
Oh, yes.
Since you're sharing the screen, so yeah.
Yeah, let me see.
Yeah, that was a project we did while I was a faculty at the University of Colorado Boulder, and now I'm at Penn State. So, yeah. So then, yeah, maybe you can walk people through what we posted here.
Yeah, so here on the project website, of course, we have the project overview description, right? Then also we have the link for all the open source models. For example, the cooling system model is in the molecular buildings library, and we also actually have some other models like CFD models, also open source released, and some other packages. And this is the technical advisor group. This is some collaborators and some press release and project report. This is a project report, and you can check out there. All the details are in the report. And so two PhD dissertations were from this project. One Dr. Fu and this is my dissertation. Okay, two dissertations, and this is journal articles we published based on this project, and some conference papers and presentations.
Okay, I think let me see any other questions. Oh yeah, there's one more question. Okay, few more. Maybe can you read the
Oh,
chat?
yes.
Yeah. Okay, go
Yeah.
ahead. Yeah.
Have you done any study on adjusting chilled water or supply air temperatures? For example, adjusting temperature just a few degrees warmer could lead to significant savings. Information I read implies that many servers are operated much cooler than the chip manufacturer required. This seems like a big saving potential. Yes, actually we did. So we changed the set point for the underfloor plenum temperature, but I didn't show here. But if you want to check out our project final report, we did have those kind of studies. We changed the underfloor plenum temperature set point. They can reach a lot of energy savings. Yeah, because the point is, uh, if you change the temperature set point for the underfloor plenum, there will be more opportunities for the system to use free cooling, right? So yeah, this is a very good question. Yes, there are a lot of energy saving potentials. So by doing this, the energy saving potential can be as high as, I believe it should be similar as 30% something, 20 to 30% energy savings. And the next question is the cooling coil validation slides had a EMBE block. Was that a custom-made component? Um, I believe not. Probably that was from molecular buildings library or from the standard library. I think it's pretty standard calculation. So if not, we can also customize the model. You just put the equation, the input, output, and put the equation in there. It's pretty convenient to
Oh,
integrate.
sorry. I think they're asking for NMB, so the block we use to calculate the error. Yeah, I think we just build it by ourselves. I don't think that's what.
Okay. I forgot. Yeah. So it's can be pretty straightforward if you learn the doctor's class. Okay, so you just define the input, define the output, and then you can put the equation. This Monadic is equation based uh, programming language. You just put the equation, and then they can calculate the NMBE based on the input, and then output the results. Okay. And the next question is, did your project look into recovery and reuse of heat? Oh, um, we, yeah, I think this question is a very good question, especially uh, in the era of more and more AI data centers are built, right? Nowadays, a huge amount of heat, right, is generated from data centers. But in our project, we didn't consider the use of the or the recovery of the heat. But if
Yeah, I just want to add a comment. Actually, later, my other PhD, Katie Hinkelmann, did include this in one of her work to
Mhm.
try to recover the heat, and then in the district heating loop, so that you can. Yeah, let me post the link of her paper to this chat window. Yeah, then we do see there's great potential to save more energies.
Yeah, I think this is especially important for the AI data centers. You think about AI data center can consume the electricity similar as like a town or even a county. You think about a huge amount of heat, right? So if they can be reused, yeah, of course there will be great potential. But the problem is we may need heating for winter, but probably in summer we don't need those heat. So the next question is, how do you ensure that the calibration data for the baseline molecular model adequately covers different operation conditions and the model remain reliable when evaluating the energy efficiency measure options? Oh, this is a very good question. Yes. So the way we did is we collected as much data as possible because we can basically download those data from their trended data. So they have the all year round data. So we try to pick the data that can cover more scenarios. But of course, then it is not um, we try to collect more data, but what we did is we just focus on a few scenarios, typical scenarios, and try to cover different operation conditions. How close was your partnership with chiller manufacturer when parameterizing model. Which type of chiller model did you use? Did you evaluate more realistic dynamic model or just more traditional ERR polynomial model? I believe what we do is based on the curve, the simplified model, chiller model. And I'm not sure what type of chiller it was, but what we did is we didn't like a partner with the chiller manufacturer. We just got the product manual of the chiller, the equipment from the building operator because they have the documented all the um, like a product menu. They shared with us. So we look at their product menu and to get those information like a nominal power, nominal like a Popper's curve. So this data can usually be obtained from the manufacturer, but we got this from the building operator.
Yeah, then we actually then we can calibrate the curve using the measure data.
Yes, we also have the measure data. Yes. And for ASHRAE decarb presentation, I just explore data center waste heat capture with, yeah, it sounds like the data center waste heat capture is drawing a lot of attention now. With the molecular buildings library BTES model in Modelica, have you seen any similar work exploring this? Probably you can check out the research Dr. just shared from a ResearchGate link.
Yeah, the link. Yeah, my former PhD student Katie Hinkman did work trying to integrate the data center into the district energy systems, which can take advantage of the waste heat for building heating.
Okay, so sharing.
Yeah, that's also a Modelica work, but very interesting. She is trying to design the system using the ENA ecological network analysis method. It's from biomimicry.
Yeah. Okay, the next question is from student. Because outdoor air dew point is typically a driver for when you can use free cooling, do you ever consider the lack of humidity as a driver? This may be more specific to an air environment. Um, so you mean the lack of humidity as a driver? Okay, I would say for free cooling of data center, the humidity is really a concern. Dry, probably they have the accepted range for the humidity. They have the lower band, the high band within like from 10 to 90% something, right? Or 85%. They do have the lower range. So, but for the climate, we analyze this Boston, right? Is humid, so we only consider uh, the humidity to control the humidity. Another question, I'm a practitioner with 17 years of experience using various energy modeling tools like Energy Plus, IESVE, okay, the IES virtual environment, right? How to get started with Modelica? Are there any course that are offered for working? Professor Zhou, probably you can answer this question. How to learn Modelica?
Yeah. Okay, I don't think that's a real official course offered for practitioner, but LBL has some training material. If you look at the Modelica Business Library website, they provide different workshops to teach people how to use Modelica. And then the tool vendors, I believe Medalon and the other tool vendors, they do have like also training sessions for professionals. You just enroll to the trainings. Then if you go to Modelica.org, the association website, you can also find some kind of maybe workshop or textbook material to teach people how to use Modelica. There's also Learn Modelica by Example, which is developed by Michael Tiller, which gives nice information. Yeah, also, yeah, the Modelica University, that's the place Yeah. So the Modelica by example, by Michael Taylor. It's great to teach people fundamentals, and then they have online access. You can just play with that.
Yeah, also share the link from the WSO's research group website. There's some the links of some resources like a free online tutorial and the introduction to of Modelica. I believe it's a book, right?
Yes, yeah. There's some free books available. Yeah. So at the university right now, I'm teaching the class the whole semester for Modelica, but it's mainly to our students, and you have to register to the classes. Yeah. So okay. Any other questions coming from? Let's see. Do we cover everything?
Yes, I think so.
Yeah.
I'm also professional working with ISVE. I believe the Modelica model can be easily integrated with the NGPlus model. Can it be integrated with ISVE model as well? Okay. So technically, so developed by LBNL. So now it's called a spawn of Energy Plus. They are integrating Energy Plus with Modelica, but I'm not sure. IESV, I think the backend engine is also Energy Plus, right? They can be technically possible, but because IESV is commercial software, I doubt they provided the interface to integrate with Modelica. I don't think it's very straightforward to integrate.
Yeah, I'm also checking now. So what happens that to enable the connection between different tools is also developed by the Modelica Association called the Functional Mockup Interface Standard.
Mm.
It's just like a English between different tools, right? So if we all speak English, then we can communicate. So FMI is a standard to enable the communication of different tools, just like English. So Energy Plus does support FMI, so that it can talk to Modelica. I think that's nearly 100 tools all support FMI. If IESVE can support FMI, then the communication will be really easy for the code simulation.
Yeah. Oh, IESV is not based on Energy Plus. Okay, it can be harder because as far as I know, the current implementation of the spawn of Energy Plus uh, is the integration of Energy Plus with Modelica. I'm not sure what is the simulation engine of ISVE, so it can be difficult to integrate Modelica, I believe.
Mm-hmm. Yeah, I think it's really towards winter. If they're able to support FMI, then it can connect to Modelica easily. Yeah. Okay. Oh yeah, Victor made a good point.
Yeah,
Yes, yeah, the
yeah,
users need to talk to the ISV
yeah.
developers. Yeah.
If they receive many feedbacks like requests, probably they can consider this.
Yes, yeah, yeah. I think we would love to also develop some training for the industry, like teach people how to use Modelica. We did write a proposal, but unfortunately was not selected. Yeah, we open the opportunity to continue working with industry to develop this kind of training material.
Yeah.
Yeah, so actually, currently at my lab, we have about 4 or 5 projects ongoing, all on data center using Modelica for different purposes. Yeah, so we actually have at least one funded PhD position, in data center cooling using Modelica. If anyone interested in that, or anyone interested in pursuing PhD in data center using Modelica, please contact us. Yeah, so this is for the fall 2026. I can post the opening link. Yeah, this year we're gonna have four fully funded PhD opens. 3 will be using Modelica. So besides data center, we also do the microgrid modeling and control. and then also large scale BD energy modeling. Okay, any other questions?
Does the sequential search still work well when the number of energy efficient measures become much larger? I think the answer is yes, because this is a simpler optimization strategy. Because actually the advantage is more significant when there are more energy efficiency measures. Because if you want to do the exhaust search, for example, you have 10 EEMs, you think about the possible combinations can be huge, right? Huge number of combinations. So if you do the sequential search, so the total searching space can be much smaller. So that means your optimization will be more efficient. But of course, it's a little bit less accurate than the global search. You basically you search all the combinations, possible combinations, but it's still a practical um, and also effective way for optimization.
Oh, sure. Actually, I would like, yeah, share something to the audience since you mentioned about your CFD work. I think that's really amazing. We should show that. Okay, since we have a few minutes, give me a second. Um, let me show that. Okay, so yeah, so this part is we developed also a fast fluid dynamics model based on my former PhD, my own PhD thesis. She did a major work on that. Maybe you can explain that. I have the slides running for you.
Oh, thank you. Yeah, so this work, so basically, um, data center, the airflow is very important because, they're cold IO, hot IO, and they're very complex air distribution. So the CFD is very important for data center. So, but the major challenge is CFD is very slow, right? Practically, if you want to use CFD to do either design or operation, so it's very slow. So what we did is called a fast fluid dynamics. So initially, the FFD was developed by Dr. Zhou, and I extended by adding more features for data centers. So this model was eventually adopted by Schneider Electric as the simulation engine of their commercial application product. And then, Dr. probably you can introduce the award we received. Pretty exciting award.
Oh, okay. I don't have slides with me right now. But yeah, I think maybe also the things you touched earlier. So the two data center we did, no, this is the baseline, right? One is in Florida, one is in Massachusetts. And then the first one is the phase one optimization with the cooling system. She just introduced using Modernica.
Yeah.
That's all the system cooling system alone. And then we worked on the airflow management. That's the phase two. But only the airflow management. You can see the savings are different. And then the phase three is to combine the cooling equipment and the airflow management together. We get the most savings. So for the one in Florida, we get about 53% saving. Massachusetts, we get about 74% energy reduction. So then, of course, this you mentioned, we coupled, and then in the Massachusetts, they they retrofit the data center. And then that's a tool Schneider commercialized, EcoStruxure IT CFD advisor. So the team, the CEO Boulder Schneider team, we got the IBIPSA Innovative Application Award this year, thanks to our work in developing the FFD model for data center. And yeah, I think that's the part she mentioned, but didn't get a chance to touch the detail. Yeah, the PhD thesis, also DOE wrote a story about our project, so you can find the information from the DOE website.
Also, there's another question. When would you consider CFD inside Modelica versus separate CFD? Um, what we did, so initially developed by Dr. Zhou, so there's a CFD module in Modelica Buildings Library.
Yeah.
So even though it's inside Modelica, but in fact, the backend engine is programmed in C. The programming language is C, is not directly implemented in Modelica. So uh, so basically we compile the C code as a dynamic link library, and then during the simulation, the magnetic model can communicate with the CFD, the C code. So um, so even though it's within Medallica, but it's not directly programmed with Medallica. So actually, it's a separate CFD model.
Yeah, it is a coupled simulation. Yeah, so let me just share the screen again. Yeah, so this is really coupled CFD. So we're running CFD and Modelica at the same time. Then we do the runtime exchange for data, so that you can do the HVAC control, and you can okay. Let's see if we can play this one. So basically, this is coupled simulation. CFD is running to simulate airflow in the room. FFD Modelica is running to simulate the control signal of HVAC systems. So the idea that we want to see how by adjusting my control. Okay, this is terrible control. You can see the chilled water flow rate is we just have on-off control. Then the supply air temperature, of course, is hunting, right? But then here is my temperature set point. I'm adjusting that, and then you can see what's happening inside the building. No, FFD is running on real time to calculate the average temperature of the occupied zone as a measured temperature. Then this will send back as a virtual sensor signal to the control for the HVAC systems. So yeah, this one is actually it's already implemented, public released in the Modelica Buildings Library. If you go to the I think it's the Zoom model, right?
Yeah, thermal zone. Yeah,
Thermal
building
zone.
the thermal
Yeah, if you
zone
go to
got a
thermal
detail.
zone, yeah, you can get this. You can actually get our FFD model and the source code. Buildings. Let's go to buildings. Thermal zone here.
Detail.
Detailed. So it's
Yeah.
right now we call it CFD, but it actually it's an FFD model. Yep. So all the work. So basically, what we did is replace the volume of air using the FFD. So we designed the entire Modelica coupling so that other CFD tool like OpenForm or Fluent can also be coupled with Modelica if someone just implement the interface on the CFD side. And she actually implemented the OpenForm coupling, right? I remember you did the OpenForm coupled with Modelica. Is that right?
Yes, when I was an intern at
Yeah.
Mitsubishi Electric, yeah,
Yes.
the interface to couple Modelica with OpenForm. OpenForm is a CFD software.
Yeah. So you can get the FFD model also on website. I can just put a link in the chat window if anyone want to look in more details. Okay, any question?
Yeah, there's one more question. I'm curious about the accuracy of FFD for large airflow domains. How reliable is FFD when simulating indoor environment like rooms or entire building spaces?
Do you want something? Do you want to answer this question?
Yeah, probably Doctor, you can answer this question because you have published a lot of paper on this topic. Like,
Yeah. Okay, so I would say FFD is coming from computer game. It's definitely not going to replace CFD because that's not the purpose. What FFD really trying to achieve is a faster speed with relatively acceptable accuracy. So we have done a lot of validation of FFD model. I would say maybe around you can get about 70 to 80% of accuracy compared to CFD, but no, 50, 100 times speed up. So that's what we're looking for. The major usage of FFD is for example, the initial design, right? So if you want to quickly simulate or try to study, let's say the data center rack placement, right? If you want to play around with that, you can use FFD. Don't have to wait for hours. So that what FFD allows you to play just like a computer game. You see the results immediately. So after you get the big picture, then you may run a more detailed CFD, waiting for 1 day or 2 days, get the results to confirm this works, or maybe do some small tuning. So the purposes are different. And so we wouldn't, okay, we would never recommend write entire building, like say if you have a large commercial building, hundred of rooms, running FFD make no sense. Really, you run FFD for the critical space, like a data center, or for example, if you want to study the lobby of the large building, right, how the airflow distributed. So that's space. But then when you're trying to do the entire building simulation, then what you can do, you can couple FFD with the multi-zone model. We also did some work. VTN, my former PhD, trying to, he coupled FFD with the zonal model so that you can, study FFD for specific zone, but then for other zones, you can just using single volume to speed up the simulation. So that work is also released in the website. The last link I gave. Okay, any other questions?
I just shared the link of the paper Dr. just mentioned. Doctor's previous student coupled the FFD with multi-zone airflow model. This is a paper.
Okay, so if no more question, let's close session here. Yeah, thank you, Xu, for your presentation. Always good to see you.
Thank you, Doctor, for the invitation again, and thank you for all the audience for attending this lecture.